Welcome to Learn with us. This is the fifth lecture of Basic Electronics.
First, we'll have a quick review of our previous lecture. In your previous lecture, you studied about Kirchhoff's voltage law, current divider rule. In your last lecture, you also understood what is Thevenin's theorem and what is Norton's theorem and how you can draw Thevenin's and Norton's equivalent circuit. Now, what are the learning objectives of this lecture? In this lecture, you will study about diodes, types of diodes. In this lecture, you will also understand what is an ideal diode and what are the terminal characteristics of an ideal and real diodes. Now, what are diodes? Diode is the simplest and non-linear fundamental circuit element. It is a unidirectional device. It is a two-terminal device having two electrodes, as its name indicates, where di means two and odes refer to electrodes. The p-n junction is the basis for diodes, certain transistors, solar cells, and other devices. Now, how many types of diodes are there? There are three types of diodes. First type is open or unbiased diode. Second is forward biased diode. And third is reverse biased diode. The p-n junction in which no external voltage is applied is called zero bias p-n junction. This zero bias p-n junction is also known as unbiased p-n junction or open or unbiased diode. As you can see here in this figure, this is p region, this is n region, and there is no external voltage applied here. So this is open or unbiased diode. Now look at this figure. This is forward biased diode in which P region is connected to the positive terminal of the battery and this N region is connected to the negative terminal of the battery. Now look at this figure. This is reverse biased diode in which P region is connected to the negative terminal of the battery and this N region is connected to the positive terminal of the battery. Now we will look at open or unbiased diode. There is no external voltage applied here in this diode. This is P region and this is N region. We know that holes are the majority charge carriers in P region and electrons are the minority charge carriers, whereas in N region, electrons are the majority charge carriers and holes are the minority charge carriers. Now, these electrons from this N region, they enter P region across this p-n junction. Now, as soon as these electrons see the hole in the p region, they get attracted and recombine with the hole near the p-n junction. Now, for each electron which is diffusing into the p region across the junction, a positive charge is created in the n region near the junction and a negative charge is created near the junction in the p region. These positive and negative charges are forming depletion layer. So this open or unbiased diode has a depletion layer at the p-n junction. Now these ions in this depletion layer, they produce a barrier potential. Now what is this barrier potential? It is the potential which diffusing carriers of both types must surmount in going from one side of the junction to the another side. Now at room temperature, this barrier potential is approximately 0.7 volts for a silicon diode and 0.3 volts for a germanium diode. Now, in an open or unbiased diode, an electric field is set up across the depletion layer between the n-type and p-type material, and the direction of this electric field is from n region to p region. Now we will look at forward biased diode. In forward biased diode, p region is connected to the positive terminal of the battery and n region is connected to the negative terminal of the battery. We know that holes are the majority charge carriers in p region and electrons are the majority charge carriers in n region. Now, when this source voltage Vs is greater than 0.7 volts, which is barrier potential for silicon diodes, holes from this p region and electrons from this n region, they begin to diffuse across this junction, which is known as p-n junction, forming the depletion layer or depletion region. Now, as a result of this diffusion, more holes are created at the n side and more electrons recombine with the holes in the p region. Now, in forward biased diode, since n region is connected to the negative terminal of the battery and p region is connected to the positive terminal of the battery, so electrons from this n side and holes from this p side, they are pushed towards the p-n junction due to repulsion. As a result, depletion region becomes thin and continuous current starts to flow around the circuit. Now look at this figure. As you can see, this depletion region becomes thin. Now when electrons leave point A, for suppose this is point A. Now when electrons from this P region, when they leave this point A in the circuit, then new holes appear in the P region. Now, due to reappearance of these holes, electrons in the N region, they diffuse across this p-n junction and recombine with these newly formed holes, and this process continues. Now, due to this heavy flow of current, reverse current or drift current becomes negligible. We know that I diffusion is the diffusion current and the direction of this current is from P to N. It is represented by ID. Now, the direction of drift current, which is also known as reverse current, it is from N to P and it is represented by IS. In case of forward biased diode, diffusion current is much more greater than reverse current, which is negligible. So, the equation of current will be I is equals to ID minus IS. So, this is forward biased diode. Now we will look at reverse bias diode. In reverse bias diode, P region is connected to the negative terminal of the battery and N region is connected to the positive terminal of the battery. We know that holes are the majority charge carriers in P region and electrons are the majority charge carriers in N region. Now, in this reverse biased diode, PN junction prevents the flow of current. Now, how it is preventing this flow of current? We know that the negative and the positive charges attract each other. So, this negative terminal of the battery, it is attracting holes from this P region away from the junction. Similarly, this positive terminal of the battery, it is attracting these electrons from this N region away from the junction. As a result, depletion region becomes thick. So now look at this figure. As you can see, this depletion region, it becomes thick since more positive ions are created in the N region near this PN junction. Similarly, more negative ions are accumulated in the P region near the PN junction. This depletion region widens until this external reverse voltage becomes equal to the barrier potential, which is 0.7 volts. Now, here this diode becomes an insulator due to thick layer of oppositely charged carriers, and here it is forming the effective capacitance. Now, in case of reverse bias diode, reverse current or drift current is much more greater than diffusion current. So here the equation of current will be I is equals to Is minus Id. So this is reverse biased diode. Here I am sharing this video link. This video is explaining how a PN semiconductor works, what is drift current, what is diffusion current, what is forward bias diode, and what is reverse bias diode. Watch this video for better understanding. Now, what is an ideal diode? An ideal diode may be considered the most fundamental nonlinear circuit element. It is a two-terminal device having a circuit symbol which looks like this. The positive terminal of a diode is called anode and the negative terminal of a diode is called cathode. We know that the symbol of diode is like this. This is anode and this is cathode. If negative voltage is applied to the anode of diode, then no current flows and diode behaves as an open circuit. Diodes operated in this mode are said to be reverse biased as they are operated in reverse direction. An ideal diode has zero current when it is operated in reverse direction. It is said to be cut off or simply off. Similarly, if a positive voltage is applied to the anode of diode, then zero voltage drop appears across the diode. Here, the diode behaves as a short circuit. Diodes operated in this mode are said to be forward biased. It passes any current with zero voltage drop. A forward biased diode is said to be turned on or simply on. These two are basically the modes of operation of an ideal diode. Okay. Look at this example. If you have one circuit like this is 10 volts, this is 1 kilo ohms, and you have another circuit like this is 10 volts and this is 1 kilo ohms. This is diode circuit A, this is diode circuit B, this is ground, this is ground. Now, first we will look at diode circuit A. As you can see, the positive terminal of this diode, that is anode, is connected to positive voltage. It means positive voltage is applied to this anode. So it means this diode is forward biased and it is obviously conducting. Therefore, its voltage drop will be 0. Now what about the current? The current through this diode will be determined by Ohm's law. We know that V is equals to IR. Therefore, I will be V upon R. We know that V is 10 volts and R is 1 kilo ohms. Therefore, the value of current will be 10 milliamperes. It means current of 10 milliamperes is going through this diode and the voltage drop is 0 volts. Now, we will look at diode circuit B. As you can see, the positive terminal, that is anode of this diode, is connected to ground and positive voltage is applied to the negative terminal, that is cathode of the diode. So this diode is reverse biased and it is obviously cut off. Therefore, its current will be 0, which in turn means that the entire 10 volts supply will appear as reverse bias across the diode. It means there are two conditions. In first condition, the circuit is open. Now in this case, current is 0 and voltage is maximum, whereas in second condition the circuit is short. In this case, voltage drop is 0 and current is maximum. This first condition is reverse biased condition and the second condition is forward biased conditions. These forward and reverse biased conditions are the modes of operation of an ideal diode. Now we will look at the current voltage characteristic of an ideal diode. Now look at this graph. Here this horizontal axis is representing voltage or V and this vertical axis is representing current or I. We know that in forward biased condition, V is equals to 0 and I is maximum. So how you are going to draw this condition on this graph? it is drawn something like this. It is on this axis. It means V is 0 and I is maximum. Now, in reverse biased condition, I is equals to 0 and V is maximum. So how you are going to draw this condition on this graph? It is drawn something like this, means on this axis. It is showing V maximum and I 0. It means the current voltage characteristic of an ideal diode consists of two straight lines. This is first straight line and this is second straight line that are at 90 degree to one another. The diode is assumed to have a zero voltage across it when forward biased, as indicated by this portion of the curve on the positive vertical axis. Similarly, since the current is neglected in reverse biased region, therefore its value is assumed to be zero, as indicated by this portion of the curve on the negative horizontal axis. So this is the current voltage characteristic of an ideal diode. Now we will look at terminal characteristics of real diodes. For this, we will understand current voltage characteristic curve of a silicon junction diode. This curve is entirely nonlinear and it looks something like this, where this horizontal axis is representing voltage and this vertical axis is representing current. This is 0. Now, this curve consists of three distinct regions. This is first region, this is second region, and this is third region. This first region is forward biased region, which is determined by V is greater than 0. This second region is reverse biased region, which is determined by V is less than 0. And third region is breakdown region, which is determined by V very much less than 0. Now, these three regions are modes of operation of real diodes. Note that in forward biased region, the current increases very little until the forward voltage across the PN junction reaches approximately 0.7 volts at the knee of the curve. As you can see here, this current is increasing very little here in this region. Now, as it is assumed that a conducting diode has approximately 0.7 volts voltage drop across it, so after this point, the forward voltage remains nearly constant. As you can see here, this forward voltage is nearly constant, but the current is increasing exponentially or rapidly here in this forward biased region in positive vertical axis. Now look at this reverse biased region. In this region, the diode voltage is increasing to the left along the horizontal axis in negative direction, and the current is increasing downward along the vertical axis. This is the off mode of diode. Now, what happens in this breakdown region? When the voltage applied across the diode is very large and negative, lots of current will be able to flow in the reverse direction from cathode to anode. So this is the breakdown region. Now, these three regions are the modes of operation of real diodes. We have studied that in ideal diodes there are two modes of operation, that is forward biased region and reverse biased region, whereas in real diodes there are three modes of operation. First is forward biased region, second is reverse biased region, and third is breakdown region. Now, look at this figure. This figure is showing current voltage characteristic of an ideal diode, whereas this figure is showing current voltage characteristic of real diodes. As you can see, there are two modes of operation in an ideal diode, which is forward bias region and reverse bias region, whereas in real diodes there are three modes of operation. First is forward bias region, second is reverse bias region, and third is breakdown region. So this is the difference between an ideal diode and a real diode. So that's all for today. Now, what are the key takeaways of this lecture? In this lecture, you studied about diodes. You understood what are unbiased, reverse biased, and forward biased diodes. In this lecture, you also understood modes of operation of ideal diodes and terminal characteristics of real diodes, where you understood current voltage characteristic curve of a silicon junction diode.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.